Hello class, welcome to our next lecture. It's on limit of a function and limit laws. I plan to introduce the idea of limits here and also discuss the laws that go with it. So to get the sense of limits, let's take a look at this function, this graph. So this is defined to be y equals f of x, which is x squared minus 1 over x minus 1. Okay, this is what you get when you graph it. So our question is, how does the function behave? Near x equals 1. So this graph looks a little peculiar because it has a hole in it, right? You see that open circle here? So you see that hole. And so our question is, we're given this function, we're given the graph, we're also given the equation of it. And then they're asking us, how does the function behave near x equals 1? So let's look at it analytically first. Okay. If you analyze this, we're told, we were asked to see what happens as we get closer to 1 when x is equal to 1. So x equals 1 is right here. So our question is now, near 1, how near? That's a question. So you're kind of looking at the neighborhood, right? You're looking around 1. And then you're wondering, okay, so then you obviously, when you look at the neighborhood, you're looking at the left and to the right. So then, in other words, I'm approaching 1 from the left, and I'm approaching 1 from the right. So no matter how I approach, from the left or the right, we need to see what is the behavior of the function. As we know, the function is a term that we use to represent many things, right? A function could appear as an equation, or as a table, or as a graph, or as a verbal description. There are 4 ways we can generally represent a function. So if you look at the representation here, the function actually is on the graph, right? The function is the graph, the red graph. Therefore, we are trying to see what happens to this red graph as we approach x equals 1. So then I would like you to see what happens to the graph closer to 1. So see where the 1 hits the graph. That 1 actually hits the graph at the hole. So the 1 hits corresponds to the hole. And so we're wondering, okay, near 1, the function has a hole. So we see that behavior. Okay. So that is a view, a look at the behavior based on our algebra knowledge. Okay. Now we have to extend this to limits. So we'll look at that. So if you did not have the hole, what value does this approach then? You see that it approaches the value 2. Okay, should be exactly 2. I'm slightly off. So as we approach x equals 1 here, down here, we see that it approaches the value 2, which is your y. Okay? Because that is your f of x, the y equals f of x. So remember, again, when I say function, I mean the graph in this case, and the graph value, the function value, would be the value that comes from the y-axis, isn't it? Where the graph hits the corresponding value or mark on the y-axis. So please understand that it's a culmination of all these things together. So it is the red graph and the function value. When I say what is the function value at x equals 1, then I'm looking at the corresponding value it points to on the y-axis, which is 2. So there are 2 things. You see the presence of a hole, and if you investigate what that hole corresponds to on the y-axis, it corresponds to 2. So this is our analytical approach. Now let's go algebraically. Okay, algebraically, what happens? So let me write that down here. So algebraically, what we do is we take the function x squared minus 1 over x minus 1, and we immediately see that it's possible for us to simplify this. Okay. Now remember, whenever we write rational functions, we always want to, it's like a disclaimer. We're trying to say where this function becomes undefined because we want to make sure that that is recorded. So for that, you have to quickly set your denominator to 0 and then solve for x, and we know that x equals 1 is the point where the denominator becomes 0. In other words, you are trying to describe the domain by showing that x should not take the value 1. Otherwise, all other values are fine. You'll still get a nice graph. Now, this is a rational function, and we've always seen rational functions to have branches, or they break off at those troublesome points. So if you look at the corresponding red graph, it is not looking like a rational, right? Meaning that you don't see the branches. It's actually a straight line with a hole. So we can kind of explain that behavior by simplifying this algebraically. So what happens is we have now x squared minus 1 is the difference of squares. So that will be x minus 1 times x plus 1 divided by x minus 1. And keep tagging this restriction along. And then you can see that x minus 1 matches with a factor above. And so you are left with x plus 1 with the restriction x is not equal to 1. What you see is that because of the simplification, your denominator is eliminated, therefore reducing it to an x plus 1, which is basically a line, right? X plus 1 is the equation of a line. But you have that restriction carried through, which is x not equal to 1. Now, after simplifying, when x takes the value 1, it really doesn't hurt the function, right? Because you get a 2. When x is 1, x plus 1 is 2. But then remember, this is a reduction of a rational function. So it did not start off as a line, but rather it is a rational function that reduced to a line. And that is kind of indicated by the hole there. The presence of the hole indicates that it's not a regular line, because a regular line, a linear function, does not have any holes. A linear function is always continuous. It's a polynomial of degree 1. It's always continuous. It's one of the qualities or characteristics of a line. But when you see a line with a hole, that is a hint for us to know that this line is actually a reduced version of a rational. Okay, so that is how we justify that the function is why the function has a hole. Okay, so let me write that story here quickly. Okay, so the rational function reduces to a linear function. Remember, rational as a ratio, the word ratio in it, and linear as the word line in it, so you know how they will behave. So it reduces to a linear function with a hole at x equals 1. Yeah. This means when you evaluate the function at 1, f of 1 is undefined. The hole says that there is a break. There is no function happening there. So f of 1, meaning the function value when x is 1, meaning the function value that corresponds on the y-axis, right? That is undefined. So even though technically you can plug in 1 and get a nice number 2, it is not accepted just because the restriction initially was set at x not equal to 1. So when it's equal to 1, it's undefined. However, we see that that as we get closer to 1, right? We saw that the corresponding y value gets very close to, if we get closer to x equals 1, I'd say. The corresponding y value gets very close to 2. So because we're doing it algebraically, now let's go further and see what's happening, how to verify this, okay? So for this, we're going to draw the table. Now we could see that it was approaching 2 graphically, but there are times when we cannot have the visual of a graph. So how do we do it? So remember, always the t-table comes in handy, okay? So I'm going to draw this table for f of x equals x squared minus 1 over x minus 1. And here I want to choose x values because we are approaching 1. So the question was, what is the behavior of the function near x equals 1? So near x equals 1, we have x values approaching 1 from the left and 1 approaching 1 from the right. So I'm going to get really close to 1 from the left. Okay, so I'll just say left of 1. Okay, so left of 1, then I am going to go with 0.9. Let's say 0.99. Okay, 0.999, because I want to get really, really, really close to 1. You should technically, even if you had like 10,000 nines there, it's still not as close to the 1, because remember, there's still infinite possibilities between that number and 1. Therefore, for calculation purposes, we try to keep it manageable this way. But technically speaking, you want to really make sure that these values are really, really large. In terms of, when I say large, I mean the number of nines must be really high. But that's okay here. Then let's also investigate what happens to the right of 1. So if it is to the right of 1, it is right after 1. So 1.1, 1.01, 1.001, right? 1.00001 and so on. That will help you get closer and closer and closer to the value 1. Yeah. So take your calculator and start computing these values. Plug in 0.9. So let's do the left of 1 first. Plug in 0.1 in the place of x up and down, okay, in the given function. So it's going to look like this, right? 0.9. I'll just show the expansion for the first one. And that's how you'll be plugging in for each x value, okay? Okay, so I have provided the values there. It's kind of convenient for this expression, right? So what you notice is, what I want you to notice is that as we get closer and closer to 1 on the x-axis, right? So as we get to the x value of 1, closer and closer, the corresponding y values get closer and closer and closer to 2, right? Let's say close to 2. There's 1.99, 1.99999, and so on. It gets really close to 2. Likewise, if you approach 1 from the right, algebraically, when you plugged in these values, you got the value 2.1, then 2.01, 2.001, so it's 2.001, which is making it again closer to 2 from the other side. So in both directions, when we kind of approach 1, right? So graphically, the function above and below, right? So it is right here, above and below, it approaches 2. Right? So as we get closer to 1, the function gets closer to 2. So this is the idea of limits. So even though there was a hole, we could actually investigate, looking past it, to see how the function would behave, because actually a hole indicates that it's undefined, and previously in algebra we said chapter closed. We couldn't just proceed any further. But here we are literally pushing the limits. That's why it's called limits, I guess. So you're literally pushing it to see, hey, we know it's undefined, but we get really, really close to it. What happens? And to our surprise, we see that it's actually pointing to a value. So in this case, the value is 2. So to kind of indicate this behavior of pushing closer and closer to this value and finding a corresponding limit value, right? This 2 is called the limit value because it approached this value, the same value, be it from the left of 1 or to the right of 1, the function value approached the same value in both directions. So we use this as a shortcut, okay? This is how we write this. This implies lim for limit of the function, right? Limit of the function, limit of f of x. And below that, we show it like this, x approaches c. So limit of the function as x approaches c equals L, okay, that's the limiting value, is a shortcut to say the behavior of f of x the behavior of the function near x equals c is L. Okay, this is a general version. So I'm going to translate this for a given problem. Okay. So for our example, this implies lim f of x was given to be x squared minus 1 over x minus 1, right? Limit of the function as x approaches 1, because we approached 1 from the left and from the right. So the behavior of f of x, the behavior of this rational function near x equals 1 is L. The L was this value 2 we found, equals 2. Okay? To say the behavior of x squared minus 1 over x minus 1 near x equals 1 is 2. Does that make sense? So we are, remember, we like to write it very concisely in math. And so this is a template. It's a shortcut for us to figure out what's happening. Instead of drawing the graph or writing it out in words, we simply say limit of f of x as x approaches c equals L. That means, we universally understand that the behavior of the function near that x value was this particular value L, capital L. So I'll just write it out as to how we read it, okay? So I'll say read as, what this limit f of x, x approaches c equals L. You're going to read it as the limit of f of x as x approaches c is M. This is how you're going to read it, okay? And it's a little lengthy to read it. It's quicker to write it, but that's how we have to kind of explain it, okay? Now we go to limit laws. So we have plenty of laws that help us to handle this. The derivation for these laws were done by some mathematicians, thank God for them. So we're just going to just utilize what they figured, and it's actually intuitive in many cases, and it involves algebraic backing to it, which also makes it even more approachable. And so we are skipping those derivations, and we will just look at directly the limit laws. Okay. So I'm going to write out the first few laws so that I can explain it to you. Okay. So as so the law says limit of x as x approaches c is c. Okay. This is an identity function. So I want you to think about this, okay? This x here, this position, right? This is the template. So you can kind of see this x position is actually your f of x. Okay? So f of x is c. This is an identity function because its identity isn't lost, okay? I'm sorry, f of x equals x, not c. F of x equals x. Its identity isn't lost because your x and your f of x will be the same value. So say when x is 1, what is f of x? That's also 1. When x is negative 2, f of x is also negative 2. So you can do it the table method if you wanted. Or by this time, because it's calculus, you must be familiar with this anyways. So negative 1 means negative 1. Negative 5 is negative 5. 0 is 0. 3 is 3, right? That's what's called an identity function. Its identity isn't lost. So when you are graphing this, so your graph will actually look like this. Okay, it's a 45-degree line. And so what we're saying is, if, say, this is 1, this will correspond to 1 as well, isn't it? And if this is negative, let's say 2, that will also correspond to negative 2 here. So no matter what, so it's some c that will correspond to a corresponding c. And that is what they mean by the limiting function. The limiting value itself is c. Okay? So no matter what part of the line you are looking at, whatever x value, that will correspond to the same y value because of the identity nature of this function. So that was the law, okay? Which means when they say it's a law or a property, we are free to use it without any difficulty, without having to explain ourselves, meaning you don't have to derive it each time. You could simply use it. Okay? So limit k as x approaches c is k. Okay? This is called a constant function. Once again, recognize that this k is your function, right? So f of x is k itself. K is some constant. So your graph would have wherever the k is. K could be 2, 3, 7, -10, -100. It could be anything, right? So say this is a k position. It's going to be a horizontal line, f of x equals k, right? So if it is 3, whatever the k is, say let's say k is 3, k will still be 3. If your x is 7, k will still be 3, right? When you plug in different values for x, there is nothing that changes your y value because there is no x in it, right? It's just a k. So it remains constant, it doesn't change. So if I have a -10, it still corresponds to the 3 on the line. So it's always going to be a horizontal line when you have f of x equals k. If you recall our introductory prerequisite topic lecture, there we saw this as the horizontal line, y equals a number. Okay, x equals a number is a vertical line, y equals a number is a horizontal line. In this case, instead of y, we have f of x. Instead of a number, we have now a constant k. Okay. So you can see how intuitive that is, right? The limit values for these specific ones. Okay. Now I'm going to give you a list of formulas that will be based on this. So say we had some function f of x. We don't know what it is. We're not telling you it is identity constant, or it could be anything. Okay. As x approaches c, let's say this was equal to L. And let's say limit g of x. Let's take another function. Okay, x approaches c. Let's say that that is equal to m. So you have two functions, and it's the same point c that we're focused on. So we're looking at the behavior of f of x as x approaches c. We're also comparing it to the behavior of g of x as x approaches c. What we notice is that f of x corresponds to capital L, and for g of x it corresponds to a capital M. So here are the rules that follow a combination of these functions. So I'd like you to see here that when you took the sum of the functions, right, f of x and g of x, and you found their limit, the limit of the combination of these functions, then it's very intuitive that the corresponding limit for the combination of these two functions will also be the sum of their limits. The sum of their functions, and when their limit is taken, corresponds to L plus M. And similarly, for the difference in the functions, you get L minus M. And I'd like you to watch this. Limit k times some constant times f of x as x approaches c will be, that constant is not going to be affected because there is no x in it to change it, right? So it's as if the k was unaffected, and it's as if you pulled it out. So you just had limit f of x as x approaches c, which is going to be k times L, KL, right? This is called the constant multiple rule. Then we'll do the product and the quotient. Now check out the eighth property, because the 6 and 7 are product and quotient, as I mentioned. Very intuitive there. This is super powerful because for the eighth property, if your function has some power, you can actually apply the limit and then apply the power, which means you can find the limit f of x as x approaches c to be the value first, which is L, and then you can take L power n. How cool is that? Where n is a positive integer, of course, and this is the power rule. And its inverse, you can say, would be the ninth rule. So that was power. This is the root. So if your function has an nth root, could be a square root, cube root, anything, right? If it's an nth root of the function, then it's as if you took the limit of the function and then worried about the root. And you know that this is the same as L power 1 over n. Okay? You can write it as a rational exponent or as a radical. We do have plenty of rules, but these are the basic rules that we begin with. And so let's look at some examples here. Okay? Okay, limit of this function as x approaches c. Well, they gave us a value c, they didn't give us a specific number. Okay, so we want to understand that this can be done using the limit laws. So you could use a combination of laws. You can see that this is a sum of three functions. When I say sum, indirectly it means the difference as well, because you can write the difference as a sum, right? So what I mean by that is you can write it like this. Plus. So I can write that difference as a sum. So in general, I say it's the sum of separate functions. So we know from the sum rule that if you had functions added inside, like f of x plus g of x, they can be separated out. Right? So I'm going to show the rules applied in nitty-gritty of it, and then eventually we will be able to do them without having to show all those steps. But we're just beginning to learn about this. So I would like you to not miss a step. So limit of x cubed as x approaches c plus. So don't think distribution, because that is a property. So, but it's as if you were distributing the limit, okay? So you are taking the limit for each function. Minus limit 3 as x approaches c. So if you recall, the rule that we used here was the sum rule, right? Now we have to apply in the next step specific rules that will help to simplify this. So this has x as the power 3. So you look at rule number 8 that says take the limit and then apply the power. So it's as if you take the limit of x as x approaches c first, and then you take the power 3 to it. Okay, whatever answer that will be, that will give you the power 3. Plus, here you have 4x squared. So you have a multiple, meaning a k value, 4, and a power. So it is 4 limit x squared as x approaches c. Okay, that's what you have here. I'm going to take it just one more step here. So this is the same as saying limit x as x approaches c, and you can take that power outside. Okay, that's permitted by the law. It is not an algebraic move. It is permitted by the limit laws. Okay, so this comes down as it is. Minus limit 3 x approaches 3 c. So I'm going to keep it as it is because there was no simplification on this one, right? All right, now it's time for us to replace all the x's by the c's, right? Wherever we see the x, we replace by the c. How do we know that? For that, we go back to this limit law, number 1, right? Whenever you have the function, you just plug in for x as c. When you have a constant, there's no x for you to plug in as c, so it returns a constant. So we're using laws 1 and 2 basically to help with this part. So this is going to be c cubed plus 4. That also becomes a c squared. Here there was no c, so it returns that constant 3. Okay? So go ahead and simplify this as c cubed plus 4c squared minus 3. And that's your answer. Now, if you were given a different value other than c, then you would compute that and multiply it. So, for instance, if you had c as 2 instead, So you'll have to do 2 cubed, which is 8, and then multiply. This is c squared, so that's 2 squared, which is 4. Multiply them out, simplify it, so you'll get a numerical answer in the end. Okay, but this was just to show you how the rules are really, the limit laws are really so helpful, so that we could actually go from here, rather here, from here all the way to here. Because all you're trying to do is plug in for x as c. Can you see that? C cubed plus 4c squared minus 3. So in order to make that jump, which we'll do eventually, I want you to understand that you had these steps in between. So, for your exams, when you show your written work, we will talk about that later. But when you do show the written work, I'd like to see these steps, okay? At least for Chapter 2 exam. Eventually, when your problem focuses on a different concept, then at that time, I'm okay if you went directly from that step to this step. Okay. So remember, when you're showing written work, we always want to see the steps, because what happens if I simply did that by skipping all these steps? Then we don't know if you did it because of algebra, because of laws. So you have to support your answers through your steps. Okay. All right. Let's look at another example. D. So the solution for this would be, first, you see that it appears as a quotient, right? As a fraction. So let's go ahead and simplify that. So very intuitively, we can use the quotient rule to separate the limit individually for the numerator and for the denominator. Support your answer by saying it was the quotient rule. When you do your homework problems too, you will see that the explanation there kind of shows you the steps, or sometimes it's explained in words if the steps were redundant, or if it was a graphical problem where you have to point to show something, then an explanation is written in words. If you want to avoid words, then you really can show the steps by following the algebraic sequence of steps. Okay. All right, here too, because again, this is the second problem, I'm trying to go, slowly here. Apply the limit individually in the numerator and similarly denominator. And then we have that one extra step where you throw the power out. So this is the most simplified form, because after that you cannot use any laws. You just have to apply the law at that point to simplify it. Okay. Now that it's in this most simplified form in the parentheses and the brackets, we'll go ahead and plug in for limit x approaches c as c. If it was limit x approaches 1, then in the place of x, you plug in as 1, right? In this case, you're replacing all the x's with c. So c power 4 minus c squared minus 1, because there was no x there, divided by c squared plus 5. So we substitute for x as c. And then we had multitude of rules that we use. We use the sum and the difference, and the power, the product, and the multiple rule, right? So we kind of, I could have shown those rules, but I expanded on those rules so you can see those rules in action. If eventually when we, kind of reduce the number of steps here and go from skip a couple of steps, then for the fact that we skip them, you have to support those missing steps by providing the rules that were used. So you can simply say product, sum, and difference, power, product, multiple rule, and so on. Okay. Anyway, so this is our answer for that question B. So get one more. C. Okay, x approaches -2. Now look at your function. Your function has a radical sign. So go for the property that allows you to handle the radical. That's your property number 9, where if you had the radical, it's as if you could take the radical out and bring the limit inside under the radical. So let me show that here. So you have limit 4x squared minus, again, minus 3 as x approaches -2. The whole thing is brought here, and the square root is applied outside. That's basically what it means. This is a root law, root limit law. So, there. And then carry that square root throughout, but then apply the limit properties in the radicand, okay, under the radical symbol. So in this step, I'm going to apply two rules together. So it's going to be 4 limit x approaches -2, and I'm going to just square that. You can't square the 4. You pulled out the 4. It's only for the x, right? And that's going to be limit 3 x approaches -2. And now we are able to... Now we don't have a c value. We now have a specific number, -2. So in the place of x, I plug in -2, and I will square it. Minus 3, because there's no x to replace. All right, so that's going to be 4. -2, the whole squared is 4. 4 times 4, 16. 16 minus 3 equals square root of 13. And that would be the answer. So when you don't have a c, you have a specific number, you see that you end up with a numerical answer. Okay? So these were some examples for you to see how we could use multiple rules, combination of rules, to present our answer. All right, now we have furthermore rules, so let's take a look at them quickly. Limits of polynomials. So this is related to polynomials. So if you had a limit of a polynomial, let's approach C, it is the same as P of C. Okay, so in that function, it's as if you replaced all your x's with a C. So if you determine that the limit of that function was a polynomial function, you can just replace all the x's by c in that function, which is technically what we could do in all these things, just that we didn't see this rule at that time, so we tried to expand it. Now, if you see it as a polynomial, recognize a polynomial in the function, you can go ahead and do that. And it's also interesting to see the limits of rational functions. So if I had, rational is a ratio of a polynomial over a polynomial. So if I had p of x over q of x as your function, then because of the polynomial condition there, it's the same as p of c over q of c. Very, very helpful. So let's take a look at some examples here. Okay. Now you see there's a quotient, right? So there are two ways to approach this. One is you see it as a quotient, and you apply the quotient rule, which we did previously, right? Limit of the numerator over limit of the denominator, and then we did individual limits for the numerator, individual limits for the denominator, and then applied the power rule, the multiple rule, and so on. But now, because we just saw the polynomial and the rational functions, the limits for them, you want to go ahead and investigate this to see if it will help you reduce some steps. So see if this is a polynomial. Yes, you do see that it's a polynomial by definition of the polynomial. And the denominator is also a polynomial. A polynomial of a polynomial means it is a rational. If it's a rational function, they say simply plug in or replace all your x's by c. So then this instantly eliminates all these steps for us, and we simply can do -1. Wherever you see x, replace it by -1. Please be careful because it's a -1. You want to make sure that you applied correctly. So please draw shells for all your x values like this, and then insert your plugged in value, the substitution. Otherwise, without the parentheses, you will be losing. For instance, let's take a look at the denominator, okay? It's -1 in parentheses with a square. If I didn't draw the parentheses, if I was so, casual about it, you see that -1 squared simply means that the negative is not squared, just the 1 is squared. So you leave it as a -1, basically. But that will be incorrect. So please bring the parentheses, and that is a valuable habit. It's not a childish habit. It's actually a very mature habit because you're trying to present to the reader, to the grader, that you are aware of the fact that you're substituting for x's that carry powers, and the powers can deflect the values by the sign, right? Okay, -1 the whole cubed would be -1. It returns a negative because of the odd power. -1 the whole squared is a +1. 4 times +1 is 4 minus 3. Take the time to do this part carefully, right? -1 the whole squared is +1 plus 5. Don't do them all in your head. Don't skip the substitution, because in your written work, you get points for showing the work, right? So you'll at least get partial credit if your answer were to go wrong. If you did everything in your head, I can only grade for what is there in the paper in your presentation. So if it is missing, then I do not know what went in your head. So I am just going to mark you wrong if the answer was wrong. If the answer is right, I'll still be suspicious because I don't know how you got the right answer without processing the steps. So please develop the habit of writing out the steps, even if you're not used to it, for the sake of clarity and transparency, particularly in an online mode. I really want to see that. So please make sure that you follow those requirements, those expectations. It's very important anyways, because even for you to retrace your steps, especially in Calculus 2 and in Calculus 3, your problems are going to be super lengthy. So you cannot just scratch it off and start all over. You could do that. Sometimes it's recommended because that way you're not repeating the error that you would made the first time. But I'm just saying, sometimes it saves you a lot of time just to be able to retrace your steps to see what you were thinking. Because I tell you honestly, this happens to me also as an instructor, that I'm looking at 3 and 2. I know I have to multiply, but I might end up saying 5, where I ended up adding it incorrectly. So it's 3 times 2, which is 6. But in your head, you know that. But when you're writing it, you are somehow processing it differently. Now, if I did not write down as 5 anywhere, I would not be able to recognize that error. And when I'm rechecking my steps with all those missing steps, I really can't catch my error and see what went wrong. It will still look right to me, right? I'm sure it happened to you too. So that's the reason why I encourage you to show your steps. All right. So the numerator gives you a 0 over 6. 0 over 6, is it defined or undefined? Again, know your rules. Never divide by 0. So if you're dividing by a 0, there is a 0 in the denominator, that is serious. That makes it undefined. 0 in the numerator and some number in the denominator, no problem. The answer is going to be a 0. And 0 is a perfectly valid answer because it is right in the middle of the number line. In fact, it balances your number line. So 0 is a perfectly fine number. Okay. Now let's try another one. Okay, once again, I recommend that you do the investigation. So it is a polynomial. This is also a polynomial. Right? Now, if you I presume that you know the differentiation between polynomials and other kind of functions, meaning your polynomials can only carry positive powers. You can't have negative powers. You can't have fractional powers. It ceases to be a polynomial then. Okay? So just remember that those are, it's important to capture those rules as well. All right. So this is a rational, okay? Now in this rational, because it's a rational one, we are allowed to substitute right away, isn't it? Okay. So I can go ahead and plug in for x as 1. So let me just show you as a way to model it for you. What I would recommend to you to do and what I do myself when I'm trying to work on a problem is I first put these shells for the x's. No matter what number you're substituting, whether it's a positive or negative number, it doesn't matter because it always is a good habit, and we've seen the importance and the game changer it can be if you missed your parentheses, right? So I'm going to show you that I'm plugging in for 1. Once I put all the shells for your wherever x occurs, then it's easy for you to compute this. So 1 plus 1 minus 2 over 1 minus 1. Do you see what happens here? You get actually a 0 over 0. This is a terrible condition, a terrible situation to be in mathematically. You don't want that. That is completely off the charts, okay, 0 over 0. Because you have the 0 in the denominator, that's far more serious. Makes it undefined. It's indeterminate, actually, because it's a 0 over a 0. So you don't have, any meaningful result coming from this. So what's the problem? We did apply the rule. We checked if it was polynomial over polynomial. We did see it was irrational. And we just used the rule, but the rule really failed us. So remember that these rules are help to simplify calculations. They're not going to be the ultimate answers for us. We still have to use algebra. That's why calculus relies heavily on algebra. So what happens here is that you can't blindly apply the law. You have to simplify a rational. That's the lesson we learned in algebra. So we see that direct substitution leads us into this disaster. So I'll just write that here. Direct substitution of x equals 1 makes the expression indeterminate. Cannot determine, right? Indeterminate. So let's simplify algebraically first. So then we have to stay in that limit form and look at your problem. It's x squared. Let me take you back here. X squared plus x minus 2. So go ahead and factor it because that's what you do with polynomials. You factorize polynomials. So use the AC method, the BC method, the X method, the diamond method, whatever method you called it. Excuse me. If it was Merced College, we usually call it the BC method or the AC method based on the books we used before. But if you are coming from high school where they could have called it as a diamond method, try to learn what that is. If none of these methods work, you always have the quadratic formula to help, okay? So we have x minus 1 times x plus 2. That's how it breaks. And in the denominator, you factor out the GCF. X squared minus x comes out as x times x minus 1, okay? So as a quick aside, okay, so polynomials means you have to factorize them if you are looking to simplify it. To factorize, we call the AC method or the method of factoring by grouping. For shortcut, sometimes we call it the BC method, which is basically your X method or the diamond method. Then we have completion of squares. That could help. Square root property. Then we have the quadratic formula itself. So in intermediate algebra, again, you can go to OpenStax, and because it's a free book, you have access to the algebra content as well. So go to intermediate algebra ebook there, and you can go over these topics there to refresh your knowledge. So this is how we factorize the polynomials. So please go over, take the time. If you feel you're rusty, if you feel like you can't recall these things, it's very, very important for you to go back and look at the ebook to go over this. As I mentioned before, this is only an overview. We are not trying to reteach algebra or go into problems purely to help you with the homework, because homeworks change from person to person. So the focus in these video lectures are to give you the concept, to break open the concept, so it allows you to think critically when faced with your specific set of problems. So here again, my recommendation is to go to the ebook and do your due diligence of refreshing your memory. Okay. All right. So here, because of the way it is, what is x squared plus x minus 2, we could use the BC method for this, the x or the diamond method, to factorize this, and then pull out the GCF. GCF is greatest common factor. So pull out the GCF. So I'll put that also here, GCF, okay, to help you out with the factorization. All right. Now, remember, whenever we have a rational that we're trying to simplify, we always want to ensure that we have our restrictions indicated here, okay? What will make the denominator 0? When x takes the value 0, it makes it 0, so we don't want x to take 0. Also, when x takes the value 1, it makes it undefined, so we don't want these two values. All other x values are totally fine except for these two. Once again, a quick aside, how do we determine what these values were? You always set your denominator to 0, okay? dr for denominator. So set your denominator to 0 to know where or for what x values it becomes 0, and therefore you will be able to eliminate them. And here we had the 0 factor property. So either x is 0 or x minus 1 is 0. So solve for each one of them. That's x equals 0, x equals 1. So 0 and 1 are the two troublesome values that will make this function go undefined. Okay. Again, these are relying heavily on your intermediate algebra concepts. So it's something that you've learned before. So please feel free to go back and remediate yourself in these concepts. Okay. I've tried to remediate here by giving you some explanation. Sometimes I've given you pointers like the ebook location. So please make use of these. Okay. All right. So now we can come back and simplify this, where x minus 1, they have to match. You know that, right? You can't just single out this x and this x. That won't work. That is totally bad. It just says that, your algebra is really, really weak, and it's going to be a very challenging time in calculus if you somehow manage through all that. I wonder how. So you cannot single out the x's. You really have to have matching, identical factors up and down to cancel. When I say factors, I mean when they have more than one expression that is being multiplied. So this x is multiplied to the x minus 1. So x is a factor, x minus 1 is a factor. In the numerator, x minus 1 is being multiplied to x plus 2. So x minus 1 is a factor and x plus 2 is a factor. We can see them very clearly because they are kind of encased or grouped by parentheses. See the importance of parentheses. Without the parentheses, it would mean totally different. So we got that. Now let's come back to simplifying this. Limit x approaches 1, x plus 2 over x. Okay. X not equal to 0, x not equal to 1. Okay. Now, x not equal to 0 is fine in the sense our real interest is not 0, right? Because your limit x approaches 1 is your limit of interest. So x approaches 1 is where you're interested. You are interested in the behavior of the function near 1, not near 0. So really, we are not so worried about the 0 at this point. Okay. So what happens here is your function is reduced. You simplified it, right? You still get a rational setup, right? Polynomial over polynomial. Kind of see that. Remember, we're doing all this because we wanted to find the limit, and when we applied it directly, we got in an indeterminate condition. Therefore, we used algebra to simplify it, and now we can plug in for x as 1 because we are now in the simplified format. So 1 plus 2 over 1. That is, so even though the restriction says x is not equal to 1, that is still manageable for us because we took care of the x minus 1 factor. That was the problematic one. And so we're going to get a nice number, 3 over 1, which is 3. So what this means is you probably will see a hole at x equals 1 in the graph. But just like the example we saw, even though there's a hole and the function as such is not defined at that point, it doesn't matter because you're trying to see what happens as we get close to it. When we get close to it, it gets close to the value 3 on the y-axis. That's what this means. Okay. So let me describe this here using a graph because this was a nice, interesting problem. Okay. So now what happens is the graph actually looks like this. Okay. So I'll give you the coordinates where it marks like that. So this was -2. One and 3, right? That's the point. This is the problem, right, on the graph where this purple graph is y equals x squared plus x minus 2 over x squared minus x. Now, when you actually do the simplification, right? When you do the simplification, what happens is you have the same graph. Okay, so we have negative 2, 1, and 3. And where there would have been a point, that's where you see a hole, because now we found that it is undefined at that point. However, we can still see the presence of a hole there, and that hole tells you that this is the reduced version of this graph, which is x plus 2 over x, right? The polynomial setup has changed. The rational function is the same, but it's reduced. So the reduced version is indicated by that hole that you see there. And so we notice that it is the rational that is simplified. So I'll just make a quick note here. The hole at x equals 1 indicates the rational function is simplified. So we found that as we approach 1 from the left and from the right, your graph actually approaches up and down towards this 3. And that's the whole point of the limit. At 1, it points to the hole, but we know it's the hole. So we are trying to see, getting very, very close to the hole from both sides to see what value it approaches. And that value is 3. What's really cool is this doesn't have to be defined in the function. We're just interested to see what value it approaches on the graph. So let's take a look at another example. Notice that the square root is only for the x squared plus 100. Okay. Now, it's time for us to see that if you were to substitute them, or if you were to separate them individually, right, and substitute for x as 0, what happens? Well, when you plug in for x as 0, okay, you get 0 squared, which is basically 0. So square root of 100, 0 plus 100 is 100. Square root of 100 is 10. So you get 10 minus 10, which is 0 on the top. And for the denominator x, when you plug in 0, you get 0. So you get 0 over 0 again, that indeterminate condition. Okay. So let's say, once again, like the previous problem, right? Substituting for x as 0, we get indeterminate form, which is 0 over 0, right? And sometimes you can even call it undefined. Okay, so it's really used sometimes interchangeably. I'd like to call it indeterminate to be a little more specific. So when you have this condition, you have no other go but to turn to algebra. That's why we really, really rely on algebra, because algebra is what helps us to simplify when we run into such roadblocks. We love the limit laws. They make life easy, but when they do not work directly, we have to then rely on algebra. So let's go ahead and think about what ways to simplify it. Now, is this a rational? Think about it. Is this a rational function? Absolutely not, because you see the very visible square root there. Rational functions are a ratio of polynomials. So if you look at the numerator, that's not a polynomial. The denominator is a polynomial, but the numerator is not a polynomial because of the square root. So that is ruled out. The only square root we saw was that last limit law related to the root. But that was for the entire function. If the entire function was a root, then that works. But here it's only partial. It's only for those two terms in the numerator that we have the square root. So what is the way around this? Well, if you recall again, it's a little challenging because it's been quite some time since you probably did this. But if you recall, under the radical chapter, radicals in your intermediate algebra, we used the conjugate method. So that is a just-in-time remediation for you here. Okay. So in your ebook, go to conjugation or conjugate. That's the concept in radicals. Okay, so go to intermediate algebra and locate radicals. What's really neat about these electronic books is that you can do searches, right? You can just type in the search box radicals and it shows up, conjugate and it shows up. So it's not like flipping through a book to figure out where it could be. So your life is so much easier in these versions. So make use of it. Now radicals, you've used this particularly in trigonometry when you had radicals of the denominator. We rationalized it, right? So rationalizing, that's another another concept that we use, rationalize. Rationalizing is eliminating the square root, basically. And we always did that for the denominator. We eliminated the radical in the denominator, okay? So the standard purpose there was to remove it from the denominator. Inadvertently, it moved it to the numerator. So you will be free of the radical from the denominator, but you would end up with a radical in the numerator, which was fine, which is fine. The reason again to eliminate the radical of the denominator is because of the limitations that radicals come with. They can't take negative values. They can't take 0. They can take 0 in the radical, but when it's sitting in the denominator, square root of 0, although that is defined, being the denominator will make the function undefined. So a lot of complications are coming from having a radical in the denominator, so we did rationalizing. But here, that is not our problem. We don't have a radical in the denominator. Our problem here is that we're getting a 0 over 0 condition. So if we can handle the radical in the top, we can move it to the denominator, provided it doesn't complicate things. So we're going to use the concept of conjugate. Okay, a conjugate is simply, just in regular English, a conjugate means to be intimate. Conjugal love is the love between a man and a woman, intimate, so that the result, the product, is a child, okay, an offspring. So likewise, in math, we use the word conjugate to indicate coming together of two terms that are equal and opposite. Okay, you've seen this again in complex numbers. Okay, So I will try to recall something more complex numbers. You had a plus bi, right? So a plus bi is a complex number. Its conjugate is a minus bi. So it's equal and opposite. So you have the same a, the same bi, but the sign in between is switched. So they're equal and opposite, right? Like man and woman, they're equal and opposite. So they're coming together. In this case, in math, they're coming together would be the product. Okay. The product of their marriage, basically. Okay, the product of these two terms. If you foiled it, what do you get? You get a squared minus abi plus abi minus bi squared, right? So these two will go away. And in this case, you take the conjugate so that you eliminate what? Because we want to eliminate the I. I is nothing but an imaginary unit. I is square root of -1. So we do that to eliminate the I, but I squared is +1. It's just the I that's problematic. So a squared minus b times -1, b squared. That's a squared minus, plus b squared. So look at that. The product of the marriage of these two conjugates is that you got a result free of the I. Okay, that's the desired outcome. So that is the idea of conjugate. You use it to eliminate something that is undesirable in that expression. It usually works only when these are equal and opposite terms. That's when you get the conjugate. Yeah. All right, so coming over here, we're going to use the idea of conjugate. And let me write this first, as it is. This is an x minus 10 over x squared. So if you look at the denominator, to think about conjugate, you need at least two terms, right? Only then you can do the opposite sign in between them. But here you have a single term. So we're not talking about the conjugate for the denominator. We're talking about it for the numerator. So for the numerator, the conjugate of square root of x squared plus 100 minus 10 would be the same thing. So equal and opposite. So in between, you'll be to bring in the plus 10 divided by x squared plus 100 plus 10. Why are we doing that? Because you can't just simply multiply by its conjugate. You have to balance it or nullify that effect by multiplying and dividing by the same thing. Right? That's what we do with LCD, isn't it? So it is how we apply the conjugate. And now life will be easy because we can see if this will help eliminate that predicament of the 0, because when you substitute 0, we have a problem. So we basically have to FOIL them. So let me show it in detail here. Now you know that in the numerator, because of the conjugate setup, it's always, you don't have to literally FOIL it. You can FOIL it, but you know that it is like a minus b times a plus b, the difference of squares. So you really don't have to FOIL and make it, larger. You simply use the difference of squares. So that is a squared, which is the first term, minus b squared, which is the second term, which is 10, over x squared times. Now you know that the radical is in the denominator. It's okay because you needed something more than the x squared, because otherwise when you plug in x as 0, it's going to make it undefined. So we are actually happy that we have that radical expression in the denominator, because it is going to add to the value of the substitution for us. All right, square root and the square will undo each other because they are opposites of each other. In the sense, they're inverses of each other. So that's x squared plus 100 minus 10 squared is a 100. Got that. Don't try to simplify anything here in the denominator because you really cannot simplify. You cannot distribute the x squared meaningfully to any of these terms. So keep it as it is. And you see that in the numerator, these go away. Okay. So you have x squared over x squared times this. So I'm going to show both of them in the same step. So that means once you got the hundreds gone, you simply have the x squared, right? So let me show that that x squared will go off with this x squared. That will then leave you with limit x approaches 0, 1 over square root of x squared plus 100 plus 10. Now you can happily substitute for 0 in the place of x. Again, remember, in the place of x, bring in the parentheses. I know it is a 0. You are already processing it and all that. I hope that eventually you'll be able to do all that. But remember that we are in no hurry because you've come all this far. You've taken all these steps. We don't want to lose it right here because we were not paying attention. All right, so that's going to be 0 plus 100, which is square root of 100 plus 10, which is 1 over 10 plus 10, which is 1 over 20. Look at that. That looks beautiful. When we did plugins directly, we got a 0 over 0, but when we took care of it algebraically, appropriately, in a valid manner, we now get a nice value, 1 over 20. Okay, so for all these kind of problems, you want to apply the appropriate algebraic technique. So if you have a rational, to reduce it, you use factorization. If you have a radical, to reduce it, like in this case, you want to use the conjugate method. And then you will always know that you're you cannot skip the techniques because you'll end up invariably with a 0 over 0 condition. So you know that you have to use a technique. Even if you forget to use it in the beginning, that 0 over 0 will kind of push you to do that. Okay. We wind up with the last concept of sandwich theorem. I've written the theorem for you here. So the detailed definition is found in your ebook, but this is more for an explanation. Now suppose g of x is less than or equal to f of x is less than or equal to h of x. Let's focus there. What this simply means is, suppose that this function f of x is between the g of x and the h of x. So this function is between two functions. And we are told that g of x, the limit of g of x as x approaches c is L. Likewise, the limit of h of x is also L. So the two ends of this inequality, they both, when you apply the limit throughout, these ends actually have the same limit L. So the function that is in between these two should also approach L. That's what this means, because because f of x is squeezed between the g of x and the h of x. It's also known as sandwich theorem, squeeze theorem, pinching theorem, all these names. Yeah. So it's squeezed between these two. It's sandwiched between these two. This again comes from algebra, right? So if the ends of the inequality are the same, then the middle value should also be the same, right? So how else can it be true otherwise? So we're using that idea here. So here is an example for you. I've just drawn a graph here, and you can kind of see how the pinching happens. So check this out. Now let's say, now remember g is less than f, which is less than h, right? So graphically, let me pick those colors too. So the bottom one must be g of x, right? Because that's the smallest of all. And this one should be h of x. And f of x, usually f of x is some kind of complicated function for which you couldn't find the limit directly. So if that was the case, that's when you use the squeeze theorem. So you go looking for two other functions between which this is sandwiched. So say f of x is a complicated function. You want to find this g and h, the green and the pink, so in such a way that your f is sandwiched or squeezed in between them. Okay. And what is spectacular about this is we want to choose functions such that as x approaches c, they all pinch at that same limiting value, capital L, on the y-axis, right? As x approaches c, the limit of all these functions, the limit of particularly h and g, the limit of h and g must be the same limit as L. That means we're saying this f of x that is in between them must also be pinched there, right? How else will your function be contained in between the green and the pink. The blue has to stay inside always, in between them always. And when H and G come together at that point C, then F also must come at that point so that they all have that same limit, capital L. Isn't that really neat? So that is this idea here. And we use this, obviously, when we have complicated expressions. It's mostly helpful in trig functions because they sometimes can get complicated. I know what you're thinking. For you, you're thinking, well, trig is always complicated, not sometimes. No, not really. I'll try to change your mind in this course. Okay. All right. So here's the example. So we are given 1 minus x squared over 4 is less than or equal to u of x, which is less than or equal to 1 plus x squared over 2. Sorry. So here, it doesn't matter what u is, right? We have no idea what u is. But we need to find the limit of this u. That's what this is. This question is saying. So this is given to us. Find limit u of x as x approaches 0, no matter how complicated u may be. Not u, the letter u. If human beings, we should be complicated. The solution would be to first apply the limit for the ends, right? Because we don't know what u is, so we have no way to apply directly for u. So we apply the limits for the ends. So this is when x approaches 0. Okay. This whole thing. So because it's because of the setup, right? You can directly plug in for x as 0. So 1 minus 0 squared over 4, which comes out as 1. Now, apply the limit for the other end, and if that also gives you 1, that is wonderful news, because then we could use the Squeeze Theorem here. So 1 plus 0 squared over 2. Wonderful. That gives us a 1, 2. Okay. Since the ends both point to 1, since limit 1 minus x squared over 4. This is how we write a step, okay? So you are applying the limit on all three parts, not knowing what u could be. What's interesting is we found that this approaches 1 and this approaches 1, right? So this implies that what's squeezed in between them should also approach 1. This implies limit u of x as x approaches 0 must be equal to 1 by Squeeze Theorem. It makes you feel really smart. I mean, it is a smart move, right? Because you didn't know what u was, but you could perfectly come up with its answer. Okay. So Squeeze Theorem or Sandwich Theorem, whatever we call it. I remember learning it as Squeeze Theorem, but the book calls it the Sandwich Theorem, so I got a little soft corner for the squeeze. Okay. All right. Well, if you wanted to look at the graph for this, you can actually check it out. Let's see. If I were to draw the grid, it appears as if one went up like this, and the other one went down like this. Okay. They must touch, right, at 0. So that's where. So when it's 0, is the other one. And it is 0. This is 1, right? This value is 1. So as x approaches 0, the limiting function was 1. And we don't know what this u is, so it could be anything notorious, right? Something like that. So this could be a u. We don't know what it is, so I tried to draw it as scary as possible. But this is for us to know that this is, this was the 1, so that is a plus. 1 plus x squared over 2. And this green one must be y equals 1 minus x squared over 4. So the trick is to find those two functions. And, with practice, with trial and error, we will usually be able to find two functions like that or to answer these squeeze theorem problems. Yeah. In this case, they gave us these two functions, so that's nice. Sometimes we just have to consider what we've seen, like from piecewise functions or things like that. In fact, the upcoming problem, that's the last example here, you will begin to see that we can actually apply squeeze theorem based on absolute value. Given negative absolute value of theta, okay, that disappeared. So we case the stuff. So given these two, you're asking us to find limit sine theta as theta approaches 0 and limit cosine theta as theta approaches 0. So for our understanding, if you want, you can draw the graph here because we are kind of familiar with these functions, right? So absolute value of theta would be more like a V shape, right? That's absolute value of theta. Negative absolute value of theta should be inverted V shape. That's negative absolute value of theta, and your sign must run in between them. And we know how the sine function behaves, right? So we know that that's going to be the y equals sine theta. And you could say this is negative pi, and this is pi. No? Then on the top, this will be 1, with a bit of 1. So instead of x and y, we now have theta and y axis. Okay? So you have to be adaptive to that, so that you're not really stuck upon. So you know that your sine theta is between these two, so you can see that it's looking great. When you do the graph, you'll get this. But even without that, you can do the problem and then verify it with the graph as well. All right, so we take negative theta, absolute value of theta, take the first condition to answer the first problem, and then apply limit to each one of them. Okay, so limit of this, limit of this, limit of this. Of course, a limit by itself makes no sense. So what is the focus on this limit? This is when theta approaches 0. So we are writing the 0 mark. Okay. And you can see from calculation, just plug in 0 there, right? For theta, that comes out as 0. This comes out as 0. So by squeeze theorem, this must also be, that's not a theta, that's a 0. That must also be 0. Okay. So then we can come here and write it more formally. Limit sine theta as theta approaches 0 is 0. That was easy. Then the second one. Again, for this, if you wanted to draw the graph, you are welcome to do that. Okay, so this is opposite 0. Apologize. In the question, I wrote it as theta, so that's a 0. 0 less than or equal to 1 minus cosine theta is less than or equal to absolute value of theta. So let's try to graph this one. Theta, and that must be equal to y. Okay, absolute value of theta, we know that that's going to be this V shape. And like the absolute value of x, instead of x, we now have theta. So, you know, that's your V shape. Of course, we should put all the arrowheads there. And 0, what is 0? Y equals 0 is nothing but your horizontal line. So you basically coincide the green graph with your x-axis. And then we know our cosine is like the V-shaped graph, right? And there you go. That is your 1 minus cosine theta. So it is, you know, it has shifted and all that. So you have that 1 minus cosine theta there. Let's go ahead and do the problem. So apply limit. Okay. So let me write this one more time. Limit as theta approaches 0. So as you can see, they all pinch at 0, right? In other words, try plugging in for 0, you'll get it. So it works perfectly algebraically or graphically. That's going to give us a 0. This will be a 0. So this must also be 0. And please make sure that you quote the Squeeze Theorem. Otherwise, why should it also be 0, right? So it saves a ton of steps, and it also gives clarity to the grader, to the reader, that you know what you're doing. So this implies limit theta approaches 0, 1 minus cosine theta must also be 0. This is your sandwich or squeeze theorem. But it doesn't stop there because it helped you to get that limit there. But you have to go further. You can go further and find the value. Okay, because let's go back and see what the question was. The question was limit cosine theta, not just 1 minus cosine theta. The question was to find limit cosine theta. So you have further steps to do. So limit 1 theta approaches 0. Separate the limits, okay? Limit cosine theta as theta approaches 0 equals 0. So when limit 1 theta, there's no theta to substitute here. So this comes back as 1 minus limit cosine theta. Theta approaches 0 equals 0. So clean it up. This implies limit cosine theta as theta approaches 0 actually equals 1. Because that was the actual question. Squeeze theorem helped us to find the limit for 1 minus cosine theta. The question wanted us to find for just the limit of cosine theta. So we had a little more work, but we got it. So that's the power of sandwich theorem. I hope you enjoyed the lecture here. I know it's a little lengthy, but you know, if we were in a class, this would be a 2-hour lecture. So we are doing good here. All right. So I hope you explore all these homework problems and utilize the concepts here. See you in the next video. Bye.